Hey everybody, it's Miss Corso. This is the lesson for Tuesday, September the 22nd. We are going to start with a quick review of where we left off in either most classes in person or where you watch this video, the video from yesterday. So this is going to be your density part 2 video. Again, we're going to pick up with where we left off with the density triangle, and then we're going to get into some pretty important density facts that you will need to know, both for your lab, for your test, and of course you just want to know in general. So here we go. We are going to practice with our density triangle real quick here. It'll be helpful if you don't have one to pause this video and go and grab yourself a calculator. Calculator is necessary for being able to calculate out these problems. So we are going to start with the density triangle. And remember, this triangle is super helpful for helping us understand, if you will, what to do when a density number is missing, when a mass number is missing, and when a volume number is missing. So if we go over to this first example here, you can see that they told you the mass is 250 grams, and you got a volume of 10 cubic centimeters, which means they're going to ask you for the density. So I put a question mark next to density. And if you go over here and we kind of think about this, it's the densities which is missing. So using our density triangle, it tells us do mass divided by volume. So in this case, you simply would do 250 divided by 10. So if I go over to my calculator, and I just minimize this for just a moment, right? Let me kind of shrink that down. I believe I have a calculator handy here. So let's hit on that. We go over to our calculator. The first one was for you to calculate out 250 grams divided by, I believe it was 10 for the volume, to get you an answer of 25. So again, if we go back, 25 is our answer. If we go back to our PowerPoint here, again, it was mass divided by volume to get your density, and your density would end up coming out to being 25, and the units are going to be grams. Since you're doing mass divided by volume, it's going to be grams per cubic centimeter. So again, the problem would be set up so that your division would be with the grams on top and the cubic centimeters on bottom. So you actually list the grams first and then your cubic centimeter. Okay, so let's go to question number or example number 2. Let's get rid of that, and we'll go back to our drawing pen, and we're going to look at example number 2. So example number 2, all right, it says basically that now you have a density. So I'm looking over here, and my density is 10 grams per cubic centimeter. And they give you a volume of 100, but now they've gone missing with the mass. The mass is what they're going to ask you. They'll say something like, an object has a density of 10 grams cubic centimeter. The volume is 100. What is your mass? So if I go over to my density triangle and I get rid of my mass, I kind of cover this over. Your D for density and your V here are left on the bottom together, and between them is your multiplication sign. Okay, so if I do D times V, I'm doing 100 times or 10 times 100, 100 times 10, same thing, right? So again, if I go over to my calculator, right, and kind of click on my calculator here, and I do 10 times 100 or 100 times 10, same thing, we get an answer of 1,000. So again, question or example number 2, you would have an answer of 1,000. So right to the mass, and again, it would be 1,000, and that would be grams. Remember, mass is always in grams. Volume will either be units, cubic centimeters, or milliliters. And your density is always going to be grams per cubic centimeter or grams per milliliter. Okay, your last and final example has your volume missing. So if I go back to my eraser here, and just make sure that that's back to normal. Go back to my pen. All right, make this, yeah, that's a good size. And we go to volume over here, right? Because we see volume is missing here, and we go to our density triangle, and I get rid of the volume, the V for volume. What's left behind is your mass and your density, and you have to divide the two. And it has to be in the order of mass goes into the calculator first, and you divide by the density number. So here I have a mass of 550 grams. I've got a density of 55 grams per cubic centimeter. So all I want to do is I want to type into my calculator 550 and divide it by 55, and I will get my volume. So again, if I go back to my calculator function, I'm going to do 550 divided by 55. So 550 divided by 55 gives you an answer of 10. So again, pretty straightforward stuff. I just kind of wanted to start with that though, because I know that in a couple classes we got cut short and in other classes we got to it, but I just want to clarify that. So again, it would be 55, and again, cubic centimeters for this, because you could see that those units were used here. Okay? So that's just the density triangle. I just wanted to, like I said, kind of clear that up for you guys. And then we're going to get into our real part of part 2, density notes today. So if we can maximize this back here again, and we're going to go to slideshow and play from the start. So we're going to kind of fast forward. This was yesterday's notes, which brings us up to here. So here's important density fact number 1. Important fact number 1 is that the density of a substance doesn't change by cutting it in half. So imagine you had your block of whatever it might be a block of wood, a block of metal, and they clearly tell you that the mass equals 6, the volume is 4, and when you divide those two, 6 divided by 4, the density is 1.5. If you took this block, whether it's wood, metal, whatever it is, and you cut it in half, what happens is the mass will change. It's now 3 for each block, right? For a total of what was 6. And your volume will also change. It'll be halved, and it'll be 2, okay? 2 and 2 here is equal to your original block, which was 4. But they change in such a way, the mass and the volume will change in the new halves of this original block proportionately. So if you do 3, which is your new mass, divided by 2, you're still going to get a density of 1.5. Same thing here. Your new block had a new mass of 3 and your new volume of 2, but again, you divide that and you get the same density as your original block. So, if we think about what density is how tightly or loosely packed your molecules are in a given area. The tightness or looseness of those molecules doesn't change just because you cut the block in half. So again, density of the two new pieces would be the same as the original piece, 1.5. Next part of this slide says, basically it tells you if an object's cut in half, its density does not change. Physical changes do not affect density. And then there was a question, basically, if you did cut the blocks of wood in half, okay, and you were to place them in this water, knowing water in here has a density of 1, where would they go? And again, if you know that the density of water is going to be 1, let me go back one. The density of this water in here is going to be 1, right? If I can escape this, I could probably draw for you and make a lot of sense here. So let's just get this back here. But again, if the density of the water in here is equal to 1, right? This is 1.0 grams per milliliter. And you throw a block that has a higher density into the water, that block, they ask you, where is it going to go? It's going to sink straight to the bottom. Things with greater density are always going to sink. Things with lower density are going to rise or float up on top. Okay, so that should answer that question. Now you're going to want to remember this fact because this fact is going to come up on your lab. It's actually going to be one of your questions. So you'll maybe refer back to this video should you need it. Okay. So again, another example of what I just explained. You got a block of wood. The block of wood is cut in half. The original mass was 20. If you cut it in half, each one of these new blocks would be 10. Your volume used to be 26, but again, halving it would mean that it's now 13. No matter if you do 20 divided by 26 to get a density or 10 divided by 13 to get a density, the density is all going to be the same. So cutting something in half, a wooden block or anything, does not affect the density. Density remains the same. So again, what happens if I cut one of the small wooden blocks in half again? The density would be the same. So the mass might be half, it might be 5. The volume would be half of 13, which would be about 6.5. And again, 5 divided by 6.5 would still give you the density of 0.77. All right, so important fact number 2. Remember, density is how tightly packed matter is in a given area or given space. Gases tend to have much lower densities than liquids, and liquids have lower densities than solids. So for most substances on Earth, most substances are most dense or have the greatest density in their solid phase of matter. Okay, so again, important fact number 2, most things on Earth are most dense in their solid phase of matter. Okay, important fact number 3 has to do with water. And water is a very unique substance because it is not like most substances on Earth. We just got done saying that most substances are most dense when they are solids, but that actually is not true of water. Water is a unique substance because it's most dense not as ice, but as liquid at nearly 4 degrees Celsius. So on the cover of your reference tables, you have a box. It says properties of water, and it gives you the density of water. And it's actually got its greatest density of 1.0 grams per milliliter at almost 4 degrees Celsius. Now, when water freezes, something entirely different happens, okay? So it is actually most dense as a liquid. It has a slightly middle, like a lower density than a liquid as ice or solid. And then water, when it's least dense, is when it's a gas, right? And explaining to you what happens with water, okay, is this is an important concept. So let's get a pen to write with. So we'll go back to black here. And if you think about it, when water is water, right, as a liquid around 4 degrees Celsius, it's got its highest density of 1 gram, squeeze a G in there, per milliliter. But when water, if you take water and you cool it down and you start to freeze it, it turns to ice. And what happens when you freeze water, it expands. And if you expand water, right, into an ice form, the molecules actually begin to spread out. Okay, and this is very true. You can even figure this out because if you have a glass of water, right, and you say, oh my gosh, my water is just too warm and I need to get some ice cubes in there. As soon as you throw the ice cubes into your glass of water, they don't sink to the bottom. They actually float up on top because they are less dense. So again, water, I'm sorry about that. Water is actually most dense as a liquid, not as a solid. So just take that into mind when it comes to answering your lab questions. Okay, all right, so we get to important fact number 4. There are only 2 things which can really change the density of a substance: temperature and pressure. If you increase temperature on something like air, okay, it'll typically allow the molecules of matter, your matter, to spread out, allowing density to decrease. Remember, density is how tightly or loosely packed molecules are. So if I compare cold air to hot air, cold air, it's much more tightly packed in here, which means it has a higher density than warmed air. Warmed air, again, allows those molecules to spread apart, and again, that in turn decreases density. Pressure is a little different. If we start to put pressure on something, imagine squeezing something together. The molecules will actually get pushed closer together, which would increase density. So again, with pressure, if you increase pressure, you're going to have an increased density. With temperature, if you increase temperatures making things hotter, you will actually decrease density. These 2 things will come up also on your lab, so I just wanted to put that out there for you so that you were okay with that. So that gets us to our final couple of slides here. So we got 4 more slides to go. First one is a sink or float. It says there are 3 beakers shown in this picture. Beaker A shows an object floating. Beaker B has an object half submerged, so it's kind of suspended here within the water. And Beaker C has an object sunken to the bottom. Give a rough estimate of what the density of each object is for each beaker. Remember, the density of liquid water is about 1 gram per milliliter when the water is about 4 degrees Celsius. So here's the deal. If we look at object A, okay, or beaker A, with object A in it, right? Let's make sure I have a pen on. When we see something floating in water and realize that water has a density of 1, whatever's floating in the water has to be something less than 1. So if I was asked to give a density of this, it looks like almost like a sponge or something, I would say anything less than 1, maybe like 0.8, 0.9, something like that. So 0.8 grams per cubic centimeter. And I'm choosing cubic centimeter because this is very regular shaped. So that's cubic centimeters, not milliliters. This one's kind of like at the top of the water, but it's kind of almost like half sunken in. So I'm going to choose something really close to water. So I know that density of water is 1. And since it's still floating, but it's kind of half submerged, I'm going to go with something like 0.9. You would even get away with saying 1.0. Again, grams per cubic centimeter. Now, this one is completely sunken to the bottom. Again, knowing that the density of water is 1, if it's completely sunken to the bottom, we got to go with something that's got a greater density than 1. So pick a number, really, honestly, anything greater than 1. So we're going to say 1.4, 1.2, 1.8, and again, grams per cubic centimeter. So again, water has a density of 1. Something that floats in water is going to be a lower density. Something that is suspended or kind of caught within the water, something very similar to the density of water. Something that sinks in water is going to be much greater density. Okay. All right, let's get to our last couple of slides. So let's erase this all. All right, so our last couple of slides. So our next slide has to do with density graphs. This will come up, and again, I just want to address this to make sure you guys know what you're doing. So when it comes to density graphs, simply a lot of times they'll show you a graph and just ask you to solve for density. So if I said to you, what is the density of this material which was plotted in the graph on the left, all I would really do is find a spot where the actual line cutting across the graph goes through the corner of a box. And if you see this right here, it goes through the corner of a box here, here. I mean, honestly, you can pick any one of these spots. So say I pick this one right here. I would go I would go down in the first case to find my mass. I'd be like, okay, my mass for that point on the graph for that line equals 200 grams. Then I would go back to the same spot that I started from, and I would go out to my, in this case, my y-axis to find my volume. And my volume here, sorry about the sloppiness, the volume here is equal to 200. So volume equals 200, and it says milliliters right up on the actual graph. So all I have to remember is density is mass divided by volume. So if a mass is 200 and my volume is 200, my density is going to equal, what's 200 divided by 200? 1 gram per milliliter. Straightforward. Same thing on this graph. If I come over here, they actually switch the mass and the volume on the axes for this graph. That's okay. If I want to find my density, all I have to remember is density is mass divided by volume. I'm going to go find a spot where this plotted line cuts through the corner of a box. So like, I'd say you got a pretty good shot of doing it, maybe like, it kind of cuts through a corner of the box here, maybe a little bit here. I kind of like this spot, to be honest with you. And all I got to do is I got to go over to my y-axis, and you can see that I'm right between 40 and 60, so my mass would equal approximately 50 grams, right? And I'm going to go down to my volume from my original spot, and my volume equals 6 cubic centimeters, so 6 cubic centimeters, and then I would go straight to my calculator and divide. I happen to have a calculator in front of me, so I'm just going to go to that calculator function. You can pause your video here if you need to, but 50 divided by 6 is equal to 8.333 repeating, so 8.3, and that's grams per cubic centimeter. There you go. That's how you use density graphs. It's so super, super simple. You just got to find a spot where, you know, on the line, you kind of cuts through the corner of a box. I find it easier there if you can. Find your mass, go back to that original spot, find your volume, and then simply divide. All right, so we are going to get to our last 2, I believe, slides. Once you're done with this video, you know that you have 8 Castle Learning questions that you're going to do. So here we go. Density of planets. This chart is actually found on page 15 of your Earth Science reference tables, and it has a column right here that says density of planets. It also includes the density of the sun and the density of the moon. The planets here are Mercury, Venus, Earth, Mars. Your first 4 planets are what we call terrestrial planets. So if you think about this, the first 4 are terrestrials. And if anybody knows the root word terre, in Spanish, la tierra, these terrestrials, T for terrestrials, mean that they're made up of dirt and rock. Your second grouping of planets starts with Jupiter and goes through Neptune. And the second group we call the Jovians. Jovian meaning that they are made up of gas. They are giant planets. If you look at the masses, they are huge numbers for their mass. as compared to our inner terrestrial planets. The one thing that they are opposite in, though, is their densities. If you look at the densities of these Jovian planets, again, J for Jovian, you see that their numbers are much, much, much lower. Whereas the terrestrials, which are made up of rock, these are much, much, much higher. So density is high here, density is low here. So it says a planet's density, of course, can be found on the Earth Science reference tables. And if we refer to our final and last slide here, it shows you a picture of our solar system. And this was a Regents question a couple years ago. It says, why do you think the terrestrial planets, again, these first four, have higher average densities than the Jovian planets? And again, this is pretty straightforward stuff. If you go back to what I just said and you think about this, right? These first four planets are terrestrials, have higher densities because they are made up of rock and dirt, which is more of a solid material, whereas the next four, which are your Jovians, J for Jovian, are made up of gases. And we should know that unlike water, most things in our solar system and universe are most dense when they are solids and least dense when they are gases. Okay, so that is our final slide for this. As soon as you are done, I would switch over to Microsoft Teams, or get back to your Microsoft Teams. Click on your link for Castle Learning. There'll be 8 questions assigned. Remember, we're going for quality work over quantity, so I'm not assigning 25 questions. I'm giving you 8. If you have to stop Castle Learning while you're doing it to refer back to this, please do. But do your best work because this does count for your class average, your quarter average. So do your be your best you and do your best work, and I will see you soon. All right, guys. Have a good one, and I will check in with you tomorrow. All right, take it easy.